Welcome to this FP2 video on de Moivre's theorem. Now, this is a very useful theorem that we're going to look at over this video and also the next couple of videos. And basically, let me kind of describe to you what it is first. So we can use Euler's relation. Now, Euler's relation is what we looked at recently, which is e to the I theta equals cos theta plus I sine theta. So we use this obviously when we were looking at the exponential form of complex numbers. So, our z equaled r cos theta plus I sine theta, or r e to the I theta. So this is Euler's relation. Now we can go ahead and use this now to find de Moivre's theorem. So this is r cos theta plus I sine theta. So this is now as a complex number. Now if I imagine, basically starting with my r cos theta plus I sine theta, and I square it, that's going to be re to the I theta squared, isn't it? Okay, which is r squared e to the I 2 theta. Now, because squaring this squares that, squares this one. Now, looking at this, kind of putting it back using up here, what I've got is r squared cos 2 theta plus I sine 2 theta. So we've basically got that r cos theta plus I sine theta squared is r squared, and then cos 2 theta I sine 2 theta. Now if I change this to the power 3, then this would be cubed, which would give me r cubed e to the I 3 theta, which is r cubed cos 3 theta plus I sine 3 theta. And if then we just said instead of numbers we used n for any integer n, then we're left with this. So r, and then brackets cos theta plus I sine theta all to the power n will be r to the power n cos n theta plus I sine n theta. And this is what's known as de Moivre's theorem, this generalization of the result. So, you can prove it, and you do need to be able to prove it. So you can prove it simply using what I've written here. So this is equal to this, which equals this, which equals this. Okay, and these valid steps then just go ahead to prove it, and you do need to be able to prove it. Now, you can also prove it using proof by induction. I'm not going to do that on this video. You can have a little look in your textbooks if you've got textbooks on this. It does show you the proof by induction. It is fairly straightforward, just setting out left hand side, right hand side, n equals 1. Assume true for n equals k, and then show basically true for n equals k plus 1, and then your conclusion. Okay, but like I said, I'm not going to go through it in this video. I haven't seen a question where it asks for the proof, I don't think, but I will have a look. But otherwise, let's get into some examples showing kind of how and where we would use this. So express this in the form x plus I y. So the first thing I want to do is change this minus sign here. So we have cos 3 pi by 7 plus I sine minus 11 pi by 7. And that is all over cos 15 pi by 7 plus I sine pi by 7. Now we want our angles between minus pi and plus pi. This one isn't, so if I add 2 pi to it, I get there's cos 3 pi by 7 plus I sine 3 pi by 7. And then the same with this bottom one. This isn't inside my normal range, so taking away 2 pi from this, and I get cos pi by 7 plus I sine pi by 7. So that's dealing with the angles. Now these are all still raised to these powers, so power 3 and power 2. Now I can use de Moivre's theorem. So remember, this is de Moivre's theorem. Now we haven't got an r in this case, but we have got the power. So it's going to be, the power will basically come down in front of the thetas. So this is now going to be cos, now I'm going to do 3 times 3 over 7 pi. So it's going to be 9 pi by 7 plus I sine 9 pi by 7. All over cos, now this one's going to be times by 2. So 2 pi by 7 plus I sine 2 pi by 7. Now, from the last video, we had Z1 over Z2 is it's R1 over R2 e to the I theta 1 minus theta 2, isn't it? So I can convert these into this form, or into exponential form, then use this and then convert them back. But basically what I'm going to end up with is cos of 9 pi over 7 minus 2 pi over 7 plus I sine 9 pi over 7 minus 2 pi over 7. This will leave me with cos of pi plus I sine of pi. And cos of pi is minus 1 plus I sine of pi is 0. So all of this just equals minus 1. Okay, so using de Moivre's theorem is for this bit to get rid of our powers. So rather than having to expand this out, we can then just create this with the angles in it, and then it makes it far easier for us to deal with simplifying in the question. Let's have a look at another example. So I've got 1 minus I root 3 all to the power 7, and I need to put this in the form x plus I y. So first of all, let's look at what's happening with the 1 minus I root 3. That's going to be like this. 1 minus I root 3. That's my alpha, and it's 1 across root 3 down. So if I work out my r first, this is going to be the square root of 1 squared plus the root 3 squared, which is going to be the square root of 4, which is just going to be 2. Now looking at my alpha, this is going to be arc tan opposite over adjacent. So alpha is pi by 3, and then theta, which is, my argument, is going to be minus pi by 3. So 1 minus I root 3 is 2 cos minus pi by 3 plus I sine pi minus pi by 3. Now, I don't need to worry about the negative angles at the moment, but let us now create this to the power 7, isn't it? So that will be 2 cos minus pi by 3 plus I sine minus pi by 3, all raised to the power 7. So now I can use de Moivre's theorem. So that'd be 2 to the power 7 brackets cos minus 7 pi by 3 plus I sine minus 7 pi by 3. So 2 to the power 7 is 128. And we've got cos. Now, minus 7 over 3 is obviously outside my range. So adding 2 pi, this will be minus a third plus I sine minus a third pi. So there I have it. Now, I didn't actually need to do this step. I could have just gone from this step straight in my calculator. Now, that's 128. Now, cos minus pi by 3 is a half. And then sine minus pi by 3 is minus root 3 over 2. So we got minus I root 3 over 2. So that gives me 64 minus 64I root 3. And that is then complete. Obviously the 128 times the half, and 128 times that half bit will leave me the 64 times the top. Okay, so that is now in this form x plus I y, and you can see how the power using de Moivre's theorem then turned into this, which was far easier to deal with than trying to expand out to the power 7. So that's all we're going to look at in terms of de Moivre's theorem at the moment. In the next video, we'll start to look at more trigonometric identities, okay, which will be, where it starts to kind of show its real usefulness to us. But until then, let's have a go at a couple of questions just using it in its basics. And before I show the questions, I just want to remind you to like the video if you found it useful so far. Subscribe if you're yet to subscribe. And if you're willing and able to help me out financially, hit that join button. So here are the questions, 5 questions, all past paper questions. Pause the video at any time to have a go yourself. Okay, welcome back. Right, let's look at the solutions to these questions. Hopefully you managed to get them all out. So question 1, express 3 plus I root 3 all to the power 5 in the form a plus bi root 3, where a and b are integers. So let's start off with 3 across, root 3 up. So we can go ahead and find out what r is, and this will be theta. So r is going to be root 3 squared plus 3 squared, and then square rooted. So that's 9 plus 3, so it's 12. So square root of 12, or 2 root 3. And then theta is arc tan, or the inverse of tan, and it's opposite over adjacent. And this is pi by 6. So I can say that 3 plus I root 3 is 2 root 3 cos pi by 6 plus I sine pi by 6. And then raising that to the power 5, I get all of this to the power 5. Which then becomes 2 root 3 to the power 5 multiplied by cos of 5 pi by 6 plus I sine of 5 pi by 6. So 2 root 3 to the power 5 is a very kind of large number. I will just leave it as 2 root 3 to the power 5 for now. So 2 to the power 5 is 32, and root 3 to the power 5 is, well, root 3 to the power 4 is 9 times then root 3. So this is like I separated the root 3 to the power 5 into root 3 to the power 4 times by root 3 to the power 1. Okay, so that's what I've done there. And that then is cos 5 pi by 6 plus I sine 5 pi by 6. So this is 288 root 3. Now cos of 5 pi by 6 is minus root 3 over 2 plus I sine 5 pi by 6 is a half. Let me turn this one into a half I. So what that means is now when I multiply these two together, the root 3's are going to kind of go, aren't they? Because root 3 times root 3 is 3. And will give me minus 432. And then plus, so a half of that, so 288 divided by 2 is 144 I root 3. So now we've got this in terms of a plus bi root 3, where, you know, a is minus 432 and b is 144. Now let's look at question 2. So we've got this. W to the power 4 would mean that w to the power 4 would be 2 to the power 4 cos pi by 6 plus I sine pi by 6 to the power 4. Now 2 to the power 4 is going to be 16, and then we've got cos 4 pi by 6 plus I sine 4 pi by 6. And I'd always put the 4 in like this before simplifying, just to show the examiner that you know what you're doing. You're using de Moivre's theorem. Okay, so try not to skip too many steps there. Sorry, I wrote the 3 and the 2 the wrong way round. So I'm left with this cos of 2 pi by 3 plus I sine of 2 pi by 3 in the brackets. So that is 16 times minus a half plus I root 3 over 2. And then times by 16, we've got minus 8 plus 8I root 3. And that is question 2 complete. Next, number 3. So again, similar to question 2, but we do have a negative value inside our brackets. So we need to change this to a minus 3 pi by 4 in terms of the angle. Okay, because that's where it works with Euler's relation. So that to the power 6, we got root 3 to the power 6, and then cos of minus 3 pi by 4 plus I sine minus 3 pi by 4 to the power 6, which is, that's 27 outside, and then we got cos of minus 18 pi by 4 plus I sine minus 18 pi by 4. I'll take the extra steps here. So minus 9 pi by 2 plus I sine minus 9 pi by 2. Now from here I could just add 2 pi's to it until I get to, an angle between pi and minus pi. Or I could just stick it straight in my calculator, which is what I've chosen to do. So cos of minus 9 over 2 pi is the same as cos of 3 over 2 pi, which is just 0. And this one is minus 1. So minus I. So final answer is minus 27i. I'm sorry, I was saying this is the same as 3 over 2 pi, but that's still outside the range. So this is the same as minus a half pi, which is inside the range. But I'm not worried about doing that here, just putting this in my calculator and getting the values out. And that's it. Right, let's move on to number 4. So first we've got to express this in the form re to the I theta. So let z equal 1 plus I root 3 and w equals 1 minus I root 3. Then mod z is the same as mod w, isn't it? Which is 1 squared plus root 3 squared and then square rooted, which is just going to be 2. So that is our value of r for both of them. Now, in terms of the angle, then z is 1 plus root 3 and w is 1 minus root 3. So that's w, that's z. Okay. So if I call that theta and I'll call that one alpha. Now what we've got is, because they're the same angle, working it out that my theta equals pi by 3 and that alpha equals minus pi by 3. Okay, and this is for that z is equal to re to the I theta and w equals re to the I alpha. So z is equal to 2e to the pi by 3i and w equals 2e to the minus pi by 3i. So that means 1 plus I root 3 over 1 minus I root 3 is z over w, which is 2e to the pi by 3i over 2e to the minus pi by 3i, which is 2 divided by 2, which is 1, and the angles taking away each other. So pi by 3 minus pi by 3i. So this is e to the 2 pi by 3i. And there we have expressed this in the form re to the I theta. Now for part B. So we want 1 plus I root 3 over 1 minus I root 3 to the power n, and we want to find the smallest positive integer value for n for which this is real and positive. So this is going to be equal to e to the 2n pi by 3i, which would be, if I use de Moivre's theorem, is going to be cos of 2n pi by 3 plus I sine 2n pi by 3. Don't need this bracket there. Now, when is this going to be real? Well, this is going to be real when this disappears to 0. Now, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, so sine of k pi is going to be 0. So when this angle equals some multiple of pi, the sine part of it will be 0, so there will be no I, and therefore this part will then give me a real value. So now I need to try some values for n. So if n equals 3 over 2, we get 2 times 3 over 2 pi over 3, which equals pi. Now the sine of that will be obviously 0, sine of pi is 0, cos of pi is minus 1. So therefore minus 1, which is real but not positive. So let's look at the next value of n that we can substitute in. So the next value of n we can substitute in will be 3, because the 3's will cancel, leaving us with 2 pi, which will be in that form. So n equals 3, so that gives me 2 times 3 pi over 3, which is 2 pi. And obviously sine of 2 pi is 0, that is the whole point here. Cos of 2 pi is 1, which is both now real and positive. So 1 plus I root 3 over 1 minus I root 3 to the power 3 is going to give us just cos of 2 pi, which is going to give us 1. Okay, and there we have done question 4. Okay, hopefully you followed what my kind of logic method was kind of describing there. Anyway, let's get into the final question, number 5. So here we've got a plus bi. Now this can be written as r cos theta plus I sine theta, or r e to the I theta. Now minus bi will be r cos theta minus I sine theta, which is r cos of minus theta plus I sine of minus theta, which is r e to the minus I theta. Okay, now let's look at them in terms of powers. So a plus bi to the power n plus a minus bi to the power n is re to the I theta to the power n plus re to the minus I theta to the power n. So this is r to the power n e to the I n theta plus r to the power n e to the minus I n theta. Now taking out r to the power n, we got e to the I n theta plus e to the minus I n theta. And putting that back in terms of cos and sine, this one would be cos n theta plus I sine n theta plus cos n theta minus I sine n theta. You know, using this one here. Not obviously this one, but this one. Now the signs will cancel with each other, leaving me with Rn times by 2 cos n theta. So we got 2 Rn cos n theta, which is real because our imaginaries cancelled, so it has to be real. And there we have it. Fifth and final question complete. Hopefully you managed that. You know, obviously you could do this in a slightly different way, so it doesn't have to be exactly what I've shown you here, as long as you've got the gist. And anyway, that's the end of this video. Don't forget to like, subscribe, join, and comment down below. Anyway, see you in the next one.